The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon and welcome to the last webinar in the 2011 ABB Protective Relay School webinar series. Today's webinar is Remote Terminal Unit Applications, and my name is Tracy Noble with ABB Power Systems. I will be moderating today's webinar, but before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question, please use the question box on the GoToWebinar control panel on the right side of your screen. We will answer as many questions as possible throughout today's event. If we are unable to answer your question during today's live broadcast, we will respond to your questions after the event. Today's webinar is being recorded, and a link to the recorded webinar will be emailed to you following today's live event. Please feel free to forward this link on to people you know who could benefit from today's presentation. And now I have a little message from the ABB Legal Department. ABB is pleased to provide you with the technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in today's webinar, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Today's webinar is Introduction to Remote Terminal Units, and our presenter is Eric Bronsdatter. Unfortunately, Ladislav was called away to a customer site, but Eric is here with us. Eric joined ABB Germany in 2009 after receiving his diploma in power engineering and a master's degree in business administration. Eric is currently serving as the North America Business Development Manager for RTU Products, and he is located in Raleigh, North Carolina. With that, it is my pleasure to introduce Eric, and enjoy today's webinar. Thanks so much.
Thanks for introducing me, Tracy, and hello everybody from my side. My name is Eric Bronsdatter, and I would like to talk about the RTU today. So what are we talking about today? These are these 6 main learning objectives, and we will start with the introduction and the role of the RTU, then coming to the trends for RTUs, as well as having an idea on the historic development of RTUs, then going on with the market requirements for RTUs, the protocols and norms, and coming then to the most important part of my presentation today, which is typical applications for RTUs. So starting with the brief definition, what is a remote terminal unit? So what are we talking about today? Remote terminal unit is different things. It can handle several tasks in the substation automation business. The first thing and the most important thing is the process monitor, means the collection and visualization of hardwired signals. The second part is that the RTU is as well a programmable device which is able to control industry processes automatically. This is what we understand with PLC, meaning Programmable Logic Controllers. The RTU is as well a communication gateway, which means that an RTU is able to handle different protocols, older and newer ones, and to transfer them to the actual needed protocols. And the last point is that today's RTUs have a human-machine interface, HMI, which offers let's say, a small SCADA system, which is the abbreviation for subrepository control and data acquisition. So now do we know what RTU is all about? And the question now is, why remote? Why remote terminal units? And there have been some trends in the recent year which are shown here. The first one is the high pressure on costs, which lead to an increasing demand for remote terminal units. Remote terminal units can lower costs in substation automation systems, and as well as the technical evolution to transfer the station automation functions to RTUs, which the technical evolution makes it possible to transfer that functions to RTUs. So we have also some technical improvements in the recent years. The first one is here, the standard communication protocols, which is for the American market DNP3, as well as IEC 61850. And in addition to this, we have here the technical improvements in direction of modern communication media, as well as standardization in hardware and software. So we have standardized softwares and hardwares which work together in one remote terminal unit independent. The use of IT technologies is another technical improvement, which means that we can use, let's say, software programs to engineer as well as to make diagnostics and maintenance with the RTU, based on the RTU. So I'd like to give you an idea which was the development for RTUs. When did it started to use RTUs? It started around 1960, and with the approach to collect data from the electrical network, which means data from switches and breakers as well as from transformers. And until 1997, we have this digital and analog data input values, and these values were sent, were collected from the RTU, and the task of the RTU till the 1960s was to collect all this data out of the network and to send it to the so-called NCC, Network Control Center. And then the Network Control Center had the possibility to send back actions or control data, so that devices like switches and breakers could be opened or closed. So let's say the RTU was or is now at the moment also a connection between the Network Control Center and available with all the devices and switches. In the beginning, mid-70s, there came up some rugged microprocessors also used in the RTU, which had the function that the hardware complexity was reduced, meaning that the former external transductors for milliamps could be replaced by internal analog and analog digital converters. Meaning comparison to the former times, we had all these external transductors, and now on it could be handled with smaller devices, electronic devices, which have been analog and digital converters. So we still had the hardwired interfacing at this time, and the hardwired interfacing at this time increased also because of these converters, of the new analog and digital converters. But at the same time, there was a big increase of RTU capabilities with these good microprocessors as well as the converters. And capabilities, for example, I noted here the time synchronization, protocols, events, communication speed, and so on. The next step was done in the 1980s as also microprocessors became famous, let's say, in the relays and meters, so in the bay level, that also different devices had now microprocessors, and there the abbreviation IED, Intelligent Electronic Device, came up the first time around the 80s. So this was the step that the substation design and complexity could be greatly simplified by interfacing the IEDs directly to the RTU. So the IEDs now had direct contact to the RTU, meaning sending all messages and data to the RTU, and the RTU then had also the possibility to act or to send messages to the devices, which said to be a new area with with new developments. And at this time, there was no common and vendor-independent protocol. Every vendor used their own protocol for the communication at the bay level. So it was quite difficult for the RTU to collect all these data coming from different protocols. In beginning 1990s, the utilities began also to install the IEDs, the intelligent electronic devices, in the distribution feeders. And this finally at the end, and this is state of the art, extended the control down to the level, to the feeder level. So it is possible now to really have control from the RTU, or let's say from the NCC to the feeder level. And the RTU has then the functionality to monitor as well as to control. So what do I mean with monitoring and control? This picture here shows exactly this idea, meaning beginning on the control level at the top, we have this network control system, which is the NCC, and then communicates directly to the RTU, which you can see in the middle. And it sends commands to the RTU in command direction, and the RTU monitors in monitor direction, sends all the information out of the process level, which you can see at the top of the slide. On the right-hand side, you have the typical applications which are connected to the RTU, which means the integrated human-machine interface with all the single-line diagrams, and you see the whole system, as well as data archives and diagnostics, and the PLC functions just as a screenshot on the right side to be able to handle program logical controllers. So what are the market requirements for RTUs? There are different market requirements coming from different application levels. The most important ones I have listed here, these are the flexible and expandable hardware concepts, so that you are able to expand your RTU as flexible as possible. And then the enhanced communication capabilities, meaning to handle with different protocols and to communicate to all the devices as well as to the network control center. Then a market requirement is the flexible communication to IEDs, meaning what I said before, not only to the control center but also to the IEDs. Then the integrated human-machine interface for station monitoring, so that you can really see your grid and see which position, for example, a circuit breaker has right now at the moment. And as well as the complex PLC functions. And then another market requirement was the modern engineering tools with data exchange interface, meaning that to engineer and program the RTU as easy as possible. Another market requirement was the archive functionality to see all what happened in the grid and what actions have been done in the past to archive this. Then another requirement is diagnosis and maintenance facilities, as well as, of course, highest possible availability, in brackets, redundant solutions, which means that if one communication unit in one RTU fails, that there's the possibility another communication unit, let's say as a hot standby, takes over. Of course, it is always really important for all customers to have a security of investment, meaning if they invest or if there's an investment at the moment that they can be sure that in the next years and next 10, 20, 30 years they will have the possibility to extend the system or to maintenance and so on. And of course, the other way around, if an existing RTU from 10 years ago or 20 years ago, older RTU is existing at the moment, that the new RTU has also the functionality to integrate the existing system and to use as much devices and for example, wiring as possible. I talked about the protocols, and here they are. These are the most important protocols we have at the moment. Modbus is an older one, and the DNP3 is the state-of-the-art protocol. Together with the last point, you can see the IEC 61850 with the Goose communication, meaning an horizontal communication between the devices and the RTU, and as well as 101, 104, and 103, which are norms to connect the RTU to devices, as well as connect the RTU to the NCC. Here I have a separate slide dealing with the IEC 61850, which is the latest norm, and it is an international norm. And this is is a norm dealing with communication protocols, and it has the idea that one system can be built out of different devices coming from different vendors but speaking the same language. So it is the target solutions. They are built with the 61850 is the parallel input and output connections mixed with a station bus, and as well as serial IED connections via different protocols at all voltage levels in the end. So you have a communication independent from the vendor. This will be a short slide concerning the network configurations. There are a lot of network configurations in the systems right now. I picked out the two different main approaches, let's say, which is centralized ring or decentralized ring. I also pointed out some advantages or disadvantages of these two possibilities to build up a network. You can see in the centralized ring that the switches are mounted together with the RTU in one cubicle, and this has the advantage that we have a short distance between the centralized communication cubicle with the RTU and the switches and the bay level IEDs, but the cable lengths from the switches to the IEDs, which are in the bay level, are normally longer than in the decentralized ring, because in the decentralized ring you can put your switches where you want, which means more near to the IEDs where you need them in the bay level at the end. So of course, if you have the RTU as well as the switches in one cubicle, it's easier to commissioning to build the system up. And the disadvantage is, of course, if there's a failure, or let's say in the worst case, a total system failure in case of fire or whatever, then your whole system breaks down, because it's all the intelligence, let's say, of the RTU and the switches and the connections, are dead. This won't happen in the decentralized ring. But of course, there are then longer distances between the station level and the bay level IEDs, and it depends on the customer requirements which solution is the best. It is always a question of the customer ideas. So now I'll come to the most important part of this presentation today. And these are the typical applications for RTUs. At the top, you can see the different levels, meaning also voltage levels, as well as, let's say, development for RTUs from left to right. Beginning in the transmission and sub-transmission, this was the classical RTU in the beginning of the development of RTUs used in the transmission level, and then going further into the feeder, which is then distribution substations, smart grids, and at the end feeder automation, which you can see in the right. Okay, which applications do we see at the moment? As I said before, for transmission and as well as distribution, we have this classical RTU idea, which means to collect all the information out of the bay level and send it up to the network control center, and as well as to automate the substation and the gateway functionality to match as much different protocols as possible. Then later on, smart grids came up, which is a well-known topic at the moment. A lot of discussions around smart grids. I will come back to this later on. And in smart grids, there was the question, or let's say the applications for the decentralized energy resources coming from wind or sun or whatever, coming not longer from other classical energy resources. So there's also the demand response, which means if there's a demand, then or checking out the demand and then acting at which point the energy demand is needed. Another application is the fault detection and isolation restoration, which can be done by an RTU, as well as the voltage optimization, all under these rooftop smart grids. In the feeder automation, we see the applications for capacitor banks, as well as ring main units and pole top RTUs, which are then connected directly to switches and smaller devices. Coming to the product solutions, to say it in general, there are different possibilities for the product solutions. The one possibility is to have a typical 19-inch rack solution, which can be built in cubicles. The smaller solution is a DIN rail solution. It's more connected to the smart grids and the feeder automation applications. And of course, there are some other solutions depending on several vendors. Here we see the classical RTU application for remote control, coming back to the levels you've seen before, we have the control level at the top, and then the station level and bay level where the RTU is located, as well as the process level at the lower end. So what do we see? Beginning at the process level in the lower end, there come different measurements and signals and stuff like this come out of the process level going into the RTU. So the RTU collects the data as well as sends commands or data to different devices in the process level. For example, for circuit breakers. And of course, in the RTU, we have these PLC functions integrated, and normally the human-machine interface to really act at the RTU, and then the RTU sends information to the control level via different protocols. You can see here 101, 104, of course DNP3 or DNP3 over WAN, which means Ethernet connections or serial connections, depending on the application level. Yeah, and of course there is the possibility to have several RTUs in one station level or bay level to build up a system depending on the process level and the amount of devices in the process level. So let's say one RTU could be server, and the next RTU could then be client and have the several IEDs as yeah, servers again under the RTU. Here we have the hybrid solution, which means we connect everything we have at the moment installed in different energy grids, which is different IOs with the protocol at the bottom right side, IEC 61850, as well as the let's say older protocols which is 103 and Modbus, and as well of course the actual state-of-the-art protocol in America, which is DNP3. In addition to all these hybrid solutions, meaning different protocols, we of course still have all these signals coming out of the bay or process level going into the RTU and then send it up to the control level. I forgot in this slide and the slide before to have also the possibility of diagnosis, meaning you can use a laptop and look at the network itself, and then have the possibility for diagnosis and see how the connection between the RTU and the control center, as well as the connection between the RTU and the process level is working, or maybe identify some problems. The gateway RTU as a communication gateway, and in this point you can see that the RTU here is connected to different control levels, which means what I explained before. You have one RTU as a communication gateway, which then can be connected to smaller RTUs, for example in the bay level. Here are no longer levels shown because it depends here on the application, and so that we have the central point two RTUs. One is the communication gateway collecting all data out of the field, and the other one database on the different protocols, and the other RTU right next beside this is the substation RTU, which for example is then collects all the parallel inputs and outputs out of the field. So there are different possibilities to bring in the RTU into a substation automation system. I talked about smart grids. Here I want to use the time to just say some words about smart grids. So starting or looking in the past, we have almost only traditional grids, which means centralized power generation and one-directional power flow from the generation to the customer. And the operation based on historical experience, meaning that in the last years or more years, a lot of people had the experience with this kind of generation, and then distributed to the end customer, which are industrial customers, as well as real households and customers like this. So what is a smart grid now? You can see it in the picture on the left-hand side. The power generation is no longer centralized. Now it's decentralized, mainly because of renewable power generation. This could be wind energy or solar energy and energies like this. And meaning that now the energy is generated not at the same place anymore and then distributed, but also the energy could be generated at an end customer, for example, with a small windmill, and then the energy flow goes in the opposite direction than before. So the customer is no longer a consumer, but also produces energy and gives this energy into the grid. So where can we find applications for smart grids? It's almost everywhere. At the wind parks, at offshore wind parks for remote monitoring and control. At the generation point of, let's say, in the energy grids for increasing grid capacity and stability. Then, of course, there's always the question, how can we store this energy? At the moment, there is no final solution how to store the energy if it is produced by wind farms or offshore parks and not used at the moment. Then, of course, efficient long-distance transmission, and as well as faster response times in the traditional energy producers at the producer sites. And the 6, 7, and 8 point is balancing load to supply and the grid operation with distributed generation, as you can see here at the generation point, and the load management and demand response, meaning to share the load as good as possible in the energy grid. After talking about the smart grids, I will say something to the feeder automation. Here there are different fields of application. One is the pole top RTUs directly connected to a switch in the bay level, and the capacitor banks, as well as the RTUs for ring main units to have the RTU connected in one ring, which is then called RMUs. Here I want to show you some real projects. This is, for example, one project from Lithuania. We have the RTU as the central point in this system, and as you can see, the RTU here is one from ABB, is also connected to an RTU from Siemens, which is another vendor, and speaks with different devices in the bay level, as well as over RAN to the NCC, which comes from GE Harris. So this picture shows, for example, how different vendors work together in one substation automation system. This picture here as well is a bigger project from Tunisia with 2 NCCs, 2 network control centers, are connected to one RTU, which acts as a gateway, and then again to another gateway RTU with IOs, with binary inputs and binary outputs, as well as analog inputs and analog outputs. And this all is then connected to the next RTU connected to the bay level, and really collecting all these information from lots of IEDs you can see here in the bay level. What you can see here also is the ABB Micro SCADA. This is a solution for SCADA systems, meaning for bigger systems, which go above the level of an RTU, and it is also connected to an antenna to get the time synchronization. So at this point, I will come to the end of my presentation, and I will hand over to Tracy again. Thank you.
Thank you, Eric, and thank you all for your participation today. As I said earlier, this is the end of this current installment of the ABB Protective Relay webinar series. We are working on the schedule for 2012, and we'll get that out to you all as soon as it's available. We do thank you so much for your participation, and hope to see you when the series starts again later this spring. Thanks so much. Bye-bye.